value applications. Let's find out how to calculate a positive distance even when one object is a moving target. Let's start with this example. Consider the distance between a vehicle that's moving and a stop along the way. If you're biking from point A to point B, and B is 15 miles away, and there's a shade tree in the middle, so let's map this out. So here's A, here's B, that's 15 miles altogether, so this is at mile marker 15, and this is at 0. At the 5-mile mark, there's a tree. All right, that's my tree. So what we're asking is, if you're biking somewhere along that path, like you could be right here, how far are you from the tree? And we need an expression for that. So the distance between you and the tree could be two different situations. Either you're biking here before you get to the tree, or you've reached some point here after the tree. And we want to know the distance between you and the tree. If you haven't gotten to the tree yet, then you would take the location of the tree, which is at 5 miles, and subtract your own location because it's less than 5. But if you had passed the tree and continued onward, then your location is some greater mile marker than the tree. And so you would do your position minus the location of the tree, which is 5. Instead of working this out two different ways, we can use absolute value to make sure that the answer comes out positive, no matter what direction you subtract in. So if you don't know where your position is, you can write an expression with the variable minus 5 and put absolute values around it. Now, even if B is a smaller amount than 5, let's say 2, you would get 2 minus 5 is equal to the absolute value of -3, and that's just 3 miles away from the tree. So we use absolute value to make sure that distance is always positive. Notice that nowhere in these expressions did I use the total distance of my journey. When you're calculating the distance between a moving object and a stationary object somewhere along the journey, this information is irrelevant. You don't need it. Let's look at a new situation. Now let's find the distance between the endpoints of the journey. This is more of a two-step problem. So let's say we're on a biking trip and there's water stations every 50 miles, including the starting location. At any point in the first 50 miles, how far are you from a water station? Since we're only looking at the first 50 miles, let's just map that out. So I start at position 0, and the maximum I get to is 50. Okay, in this situation, you're biking along this path, and instead of looking for the distance between you and some object in the middle, we want to know how far are you from water. And you always want to find the distance between you and the closest water station. Okay, so you might be there, or you might be located somewhere over here, and then we would want to know this distance, right? So we're looking for the distance between you and the closest water station. In the first example, that would be B minus 0, which is just B, right? And in the second situation, we would want to know the distance between you and the 50-mile marker, so we'd do 50 minus B. Notice how different these expressions are. We can't just put one of them in absolute values. It wouldn't turn into the other one. So it's not just a matter of order this time. Now we have two different targets, and we want to know the distance between us and whichever one is closer. This is a little more complicated. But imagine this. Let's take that same map and look at what's going on. As I travel along my path here in this direction, notice this distance gets bigger and bigger, right? I get here, it's a little bigger. I get here, it's a little bigger. But when I get to here, suddenly the distance between me and the water got smaller because I crossed over the midpoint right here, the 25-mile marker, right? Which is the midpoint in my journey. Now I don't want to know the distance between me and the midpoint, really. I want to know the distance between me and the water. But the midpoint is important. Imagine folding the journey in half on the midpoint so that 50 becomes the same as 0. Now I have this diagram. Here's 25 miles. Here's 0 or 50. What I really want to know is how far am I from either of those, which is sort of the opposite of asking how far am I from the midpoint. And that's what we did in the previous example. What we're going to do now is we're going to use what we learned about the distance between us and some point along the journey here, and then subtract that from the maximum distance this could be to see how much is left. Here's what I mean. We already know the distance between us and the midpoint is b minus 25, but the absolute value, because we don't know if we're before the midpoint or after the midpoint. So that gives us the distance between us and this region right here, either here or here. Notice that the maximum distance I can ever get from a water station is 25 miles, because once I travel more than 25 miles, I'm getting closer to the second water station. So it turns out that the maximum distance is the halfway point. So what I'm going to do is subtract this distance and see how much of this distance is left. The way you do that is you take the maximum distance you could be away from your target on either end and subtract the distance from the midpoint. So at any point in our journey, the distance from the ends of the journey would be equal to the maximum distance you can get from water minus the distance that we are from the midpoint. Now let's add something a little more complicated. What if we think about rate and time and not just distance? Well, right away when rate and time are involved, you need to remember your distance formula so that you can use it at any moment, okay? In this case, the rate is 1/2 mile per hour, so remember that. Now let's reconsider our two situations. In example A, we're talking about a distance from a tree that's 3 miles into the journey. But this time, instead of knowing our position along the journey, we're going to relate it to how many hours have gone by. So we start with what we did before. Here's the beginning of our journey, and here's where the tree is located, and we're at some position along the way. The distance between us and the tree would be normally equal to our position x minus the position of the tree in absolute values, to make sure it's positive even if we're before the tree compared with somewhere after the tree. But in this case, instead of our position x, which was distance, we're going to use h hours and 0.5 miles per hour. So our position along the journey is equal to 0.5 times however many hours we've been traveling. So we're going to substitute this. So the distance turns into absolute value of 0.5h minus the position of the tree. And that's the change when rate is mixed in. Now let's look at the other example, the distance from the start or finish of a 10-mile hike. Okay, in this case, since we want to know our distance from either end point, we need to consider the midpoint. So really what we're saying is this distance from here to us is the difference between 5 and how far we are from 5. Our basic formula for that was half the distance, which is the maximum you can get from either endpoint, minus the absolute value of how far we are from the middle, which was x minus 5, okay? But remember, x was position, and what we want is distance calculated based on hours. So we use our same conversion. Our distance from either endpoint of the hike is the maximum distance from either end minus how far we are from the middle. But in this case, we substitute rate times time to get our position along the path minus the location of the midpoint. And that gives you how far you are from the closest endpoint of the hike. Now let's reconsider the hot air balloon problem from the homework.